point P and a vector attached to it. That's it. Okay. Then I can do what? At one point I can have zillions of what do you call vectors attached to it. Okay. So all these are what do you call by definition tangent vectors. So I'm going to denote TP Rn, okay, as the tangent space okay. And what does it mean by this? So it's the set of all tangent vectors at P, will be attached to P. So I guess it's a collection of all its P's actually. Okay. We can show it has a nice structure. It's a vector space. Maybe a good exercise to do. Okay. Exercise to do. Prove Rn is a vector space. Okay. It's a vector space. I'm not going to tell you the what do you call operations under which it is vector space. Try to figure out for yourself that okay, what should be the operations on. In other words, what would be the meaning of adding two tangent vectors? Okay, and obviously the result should be a tangent vector. So what the key thing is. Okay, so try to define an operation on it, and then prove it that it's a vector space, or at least prove it that it's well defined. Those operations are well defined.
So will this coincide with the previous notion of tangent vector that we had?
Yes. Obviously, it is going to. We're going to use it actually as the previous one. Okay. I'm going to use some term which are pretty sophisticated meaning, but I want to introduce them here, and that's a good idea actually. That when we will, for example, try to define the same things on abstract spaces, at least you would have an intuition that what we are talking about actually. Okay. The next thing that I would like to tell you is something called the tangent bundle. Tangent bundle. Okay. Now, what do you mean by a tangent bundle? So I'm going to denote it by TRN, or maybe tangent bundle. Okay, at M, where M is some part of Rn. So it is what? It is the union of all disjoint tangent spaces that you can draw and the people on side. Okay. So you take all those points which are inside them, okay, and take their tangent spaces and put them together, so it will be what you call the tangent bundle. Okay?
It's not a vector space.
And it's not a vector space. But it has a very good structure. It has some other good structures actually. We're going to see it later. Okay. I don't know whether we'll have time to see it, but at least. So what's a tangent bundle? So it's just simply take the union of all those tangent spaces which are inside. Okay. Now the phases have they're very funny and clever way to visualize things actually. Sometimes amazes me that how the heck they are putting things actually. So let's try to do what? let's try to put before making this picture, is there any confusion in I'm going to spend time on doing examples and some exercises about these, okay? So that you should have also an intuition. You want to understand, for example, this theory in detail actually. So with this book, what do you call, by Barrett O'Neill, you can read, I think, first two sections. Yes, first two sections. Section 1.1 and 1.2. So it talks about tangent vectors and in detail and so on and so forth from me. Okay. But it doesn't talk about tangent vectors. But tangent vectors in detail. Algebra, examples and some exercises. I'm going to put some things based on it. Now, if we have tangent vectors and what do you call notion of vectors here? So let's try to define. So can you see here? कितने लोग हैं देख सकते हैं? ठीक है? समझ आ रहा है? नजर आ रहा है? So I'd like to define what do we mean by vector field. So what was the vector field that you learned at calculus?
Function from Rn to R.
So we denoted by the capital letters. And we said that okay. So any map from Rn to Rn, or does it have any?
Rn to Rn.
Rn
Into M.
Yes, and
Rn to Rn.
Rn to Rn.
But that's a vector function.
That's a vector function. So it's like which takes the points inside. Okay. What do you call? Takes the points, static points actually. Okay. So that's from your multivariate calculus. I would like to, because based on this intuition, I'm going to define things there. So give me a point which is P1, P2, and Pn here. Okay. So are you going to get what? So it's a static point. It's just a point in the space actually. While on this side, you don't get a point in the space, but you get a collection of points in the space actually, which are defined through some function. Okay. So in other words, this guy is going to be a vector. Okay. But the vector in each vector, so it's like you have this scale of functions. I say it again. So F2 and Fn actually. Okay. So if this point is P, okay, then all these are evaluated at P as well. So these are now functions actually. So you're not getting one just function. One static vector, but you are getting a bunch of, what do you call it, where Fi's are what? So like Fi's are the maps from Rn into Rn. Okay. Give me an example of it. So what would be the example of x, y equal to
Vector
X plus y.
x plus y and x minus
plus
y.
y, x minus y. Okay, something like that. That's an example. So, are you getting the point? This is kind of a continuous assessment, assignment of points to the space. Vector fields are pivotal here. Okay. Why you need vector pivotal? We discussed this in calculus. There are things that you can model through scalar fields and scalar functions, but there are things which can't be understood through scalar fields. You need vector fields. For example, you want to track the trajectory of, for example, a particle in moving fluid. Okay, so what do you call that? That particle directions all the time, changing directions. You getting it? So in other words, it's going to have a certain, magnitude, okay, jump and a direction basically. Okay, and maybe every particle of a, what do you call, fluid has a certain direction, okay, and a movement assigned to it. So, and what other could be the example? Scalar fields के क्या होंगे examples? What could be the examples of fields? So temperature is, ठीक है, what do you call, prototype example. But what would be a non-trivial example of a scalar field?
Volume.
Fluid volume, तुम तो बता दो. Density. Density of a fluid at any time t is, because a fluid can have a various density. It's a scalar field. Current, flow of current actually.
Sir, when means the physical quantity जब वो scalar हो, तो हर point मतलब वो scalar field है.
So in other words, vector field means that, okay, you have a part of a space and you are assigning every single part a vector actually. And that vector has a physical meaning. Okay, and scalar field is going to be something similar. Okay, you have a part of the space in which every point is associated with a real number actually. Okay, so for example, if you have a pretty sophisticated, too much sophisticated thermometer, something temperature measuring device, you just move it around, you will see that even the same room has a various, what do you call, temperatures assigned to it and linked to it actually. Are you getting the point? Okay. So what's a vector field? A vector field. So imagine that a U is a subset of Rn, okay, and for us vector field is X, which is the map from U. Have a guess. What must be that? So you want to assign vectors to it, okay? But we have now introduced a very particular kind of vectors actually that we are interested in. So tangent vector actually. So not just the tangent vector, but a tangent bundle at U actually. Okay. So the tangent bundle actually. Okay. For us, so it could be any vector. So it's like, okay, you pick a point from U, okay, and assign it a tangent vector, but that tangent vector it can be at any point, and it is going to be in the tangent space of any point in U actually, at that particular point in U. Okay, are you getting the point? So one of the difference that you can already see here, that we are not dealing with the vectors, we are dealing with the tangent vectors all the time actually. For us here, the vectors are tangent vectors. Okay, are you getting the point? Okay, so they have some origination, or origin, and they have some vector attached to it actually in the classical sense. Is it making sense? So it's a map. So X from, which is a map from U, which is a part of Rn. Okay, interestingly, he's not writing Rn, he's saying U belongs to Rn. Okay, but okay, let's not lose too much originality of our mathematics. So it's okay, is vector field if it's smooth. If it's smooth. Okay? And smooth in what sense? Smooth in this sense. So in other words, X belongs to the C infinity. So it will be a vector field. So we want vector fields to be differentiable. Okay?
Each component.
Because we want to play with them. Okay? Differentially. In the terms of calculus actually. Okay? Is it making sense? So any map which is smooth and takes values from some part of Rn and put them on some tangent vector, assigns them some tangent vector, you're going to say that okay, that vector is a vector field. And if you see essentially, this, like the case that you discussed there just become a particular case of it actually. It's the same thing. This is motivated from the same thing actually.
Sir, can you write the pre-image and image definition?
Yeah, I'll write. I'll do the algebra of it. Forget to put it. I'm just, at the moment I'm not doing algebra, just defining definition. And then I'll do the algebra of it actually. Now I'll do the basic properties of it. Okay, is it making sense? Okay. So, how does the tangent vector look like in classical case actually? In this case, how does the tangent vector look like? Tangent field, vector field look like actually?
Sir, gradient.
So you can have like one typical example in that, it's like a funny.
Yes.
Okay. For teaching geometry, you should have very good skills of drawing actually. Very bad at it. I don't know how I'm going to manage it. You have to be patient. Okay? Something like that. It's like every point, fictitious point has, obviously like this part of the space has a lot of other points, but just assuming that okay, there's going to be something like that. Okay. So that was the picture in the classical sense. But how to picture this guy? So that would be a pretty hard challenge actually. That, you have a map which is smooth and throwing things into the tangent bundle. No. So let's do it. So the physicists have their clever ways to put things. Shall I make it there actually? So it says this actually. It says this. Says that imagine this is your U. Okay. This is your U. And U is part what? It's a part of Rn. Okay. This is your U, some part of Rn. Okay, it's an abstract place. It's not line. The Euclid's line, fictitious. Okay. Some people call him faker. I think it's not a good thing to call him a faker because he has done a very good job actually. But anyway, because why they call him? Because they call him a faker because he put on paper something as real, something that only exists in his mind actually. Not something the real, but you're just so you have this thing in your head. And you are pretending it to be the real actually. I'll take the side of Euclid. I'll say, what else the method you have actually. I think it's a pretty good start. We must appreciate it. Anyway, so imagine this is your U or M, whatever you want to call it. I mean, in this picture, so it calls it M, for example. Okay, this is M. So M is a part of Rn. So obviously M is going to comprise of the points actually, P1, P2, P3 and so on and so forth. Okay? And on each point you have so-called tangent space. So let's denote that tangent space, they call it a folium actually. So they have a sophisticated name for it. So let's see that this is the folium or maybe the tangent space. Okay? At the point P1. As I said, that's not a real picture. So obviously, Rn is a pretty complicated manifold. Okay? That's what you call the folium actually. Okay? Folium are the okay? The tangent space. So if I have an abstract point P here, this represents PP Rn. What would be tangent bundle?
So the union of all these.
So union of all these. So it's like you combine all these, put them together. So that's your essentially what you call tangent bundle. Are you getting the point?
Yes.
Okay. And how does the vector field is going to look like? Okay, so in this line every point is not a point but it's a tangent vector actually. Okay. So how does the vector field is going to look like? Okay, take a point from here and take a point from here and take a point from here and that's your vector field. And obviously you combine all these sticks and you get what? The tangent bundle. So any vector field is something which is going to take all these points obviously, okay, and throw them in some tangent space. In other words, it's going to, so X is going to what? Is going to take P1 and put it, map it onto some tangent vector actually on this folium. Are you getting the point?
So जो डॉट बनाया आपने उस फॉलियम पे वो x of p1 है ना हमारे पास?
Yes, of P1.
So ऐसे आते जाएंगे पॉइंट्स हमारे वेक्टर्स.
ठीक है? अभी करते हैं एग्जांपल. But obviously, one of the limitation is there that okay, you can define things abstractly, but to do example, you have to return here in this real world.
सर पर्टिकुलर ये इसका बन जाएगा. आप ये कह रहे हैं ना ये उसका पर्टिकुलर केस है.
I'm saying that okay.
वहाँ पर smoothness.
So I think there was some conditions here. It's not just every map is a vector field, but there was some differentiability things basically there. I think there was some differentiability condition here. Just check out the books. As I said, better pick out your calculus book, okay, chapter 1, 2, 3, and give them a quick go actually, because I'm not gonna spend too much time on the things that we have done already. Okay. ठीक है जी. Is it making sense? Challenge. So let's get into the real world. Okay. From this abstract world. So if I summarize what we have done so far. So what we did, whenever we will say a vector, we mean tangent vector. And whenever we mean tangent vector, we mean a vector which originates from some point and has some vectorial part or vector in classical sense. So this vector which is attached to the point P is in the classical sense. It has three components, I, j, k, or whatever, some components, okay, attached to it in a classical sense, okay. Scalar fields, P4, and vector fields are basically the maps from, the part of Rn to the tangent bundle. All right. So let's do the algebra of now tangent vectors and the vector fields actually. And let's try to convert them into computation. Before I forgot, I must tell you something. There's a brilliant resource. You want to see differential geometry in classical sense. There's a channel. I hope that you all know NJ. I think Wilsberger, something like that. There is this Australian guy who is a skeptic of infinity and hence real numbers. So real numbers do not exist. So he's a very funny guy. And a brilliant mathematician, obviously. Or at least he's a brilliant, what do you call, explainer of things.
Illustrator.
So he has demonstrated. He's an amazing demonstrator. So here the course on differential geometry. Not long lectures like us, just 40 minutes, 45 minutes, something like that always. Okay? So I will keep on referring things from here and you have to see them. So that would be kind of, we call assess part. So for example, for this week I would say that you must see its lecture 1 at least. Okay? Because he introduced a lot of classical curves. And I'm going to follow, his approach in some cases as well. Okay, so lecture 1 he introduces lots of classical curves and how they come into existence. And he's a very good historian as well. Or orator of the history, narrator of the history.